So good afternoon, everybody. I want to thank the organizers for the invitation. So it's a nice opportunity to think about the future of the field in instrumentation. What are the new multi-beam receivers? What is achievable in the future? So I will start just with a brief introduction of the field of instrumentation for millimeter and sub-millimeter waves. So what is not mentioned in the title, and I should have, is this is mainly for high spectral resolution, very high spectral resolution, meaning that's heterodyne technique. So I would describe the current state of the art, what is achievable now, where do we come from, and illustrate some of the current projects and ongoing developments in various telescopes. And then try to think a bit what will happen in the next 10 years and beyond. Where can we go? What is feasible? So just as an introduction on the instrumentation in millimeter waves, sub-millimeter waves, there are two main families of instruments existing. So we have the incoherent detectors that are used for continuum observations for instrumentation. So they usually are sensitive to very wide frequency bandwidth, and then they have possible spectroscopic capabilities. They can have mid to high spectral resolutions with filters and other schemes to really narrow the frequency that is being resolved. To get really to the very high spectral resolutions, we need to go to coherent detectors. One technique for that is called Heterodyne Instruments, where we have to mix with another local oscillator, and this allows really to get to the highest factors. So just to put to recall people, probably not needed here, but the resolving power is defined as then the frequency of observations divided by the frequency resolution that you're achieving, is R factor. What we call mid to high resolutions is 10 to the 3, 10 to the 5. So this is achievable with these continuum detectors. So there are various techniques for these detectors. So transition edge sensors, kinetic inductance detectors, bolometers, or one of the first ones, for instance, germanium based. All of those different detectors, then they can be coupled with gratings, Fourier, Echelle diffractions, Mach-Zehnder Fourier transform spectrometers. For instance, PAX, Spires on Herschel use those type of techniques. On SOFIA, Airborne Observatory, the XS instrument has a echelon reflection grating. And also on SOFIA, for now, post-project Hermes was having also Fabry-Perot interferometers, aiming to get to 10 to the 5 and even slightly higher than that. So this is to show what is achievable with these techniques. And with heterodyne, with coherent detectors, we can go higher than 10 to the 6. So just to give some examples, at 230 gigahertz, if you want to resolve details finer than 100 meters per second, then you need a backend resolution. When you digitize, when you sample the analog signal, we have backends with 32 kilohertz. That gives you R 10 to the 7. And even going even more sensitive, more finer than that, Vespa backend at the 30 meter at ERAM with 3 kilohertz resolution, it gives 10 to the 8. So this is among the highest numbers that are achievable. So after this introduction, I just want to, before I start with the heterodyne work, illustrate a bit what happened with the continuum instruments, how they evolve with time. So I think it's interesting to see how in 30, 40 years they really went from few pixels in the 80s to now over thousands or routinely made. So we are now at the scale that the arrays have 10,000 pixels for continuum detectors in the millimeter, sub-millimeter waves. Just will illustrate the ones I know here from the Max Planck group of Ernst Kreiser, that from between 80 and 2010 at the 30 meter and then at Apex, they went from few pixels to 300, and also show that the current state of the art, or for instance, the MKIDS arrays at the NICA 2 at the 30 meter also, or Scuba 2 with transition edge sensors in the years 2000, 2010 at JCMT. just also mention that Apex has a project of 20,000 pixels, the AM key that is still not installed, but it should be at some point. Then to show you the evolution for the 30-meter bolometers from the 80s to the 2000 something. We went from 7 pixels to 19 pixels. Then Mambo 1 had 37 pixels. Mambo 2 117 pixels at 1.2 millimeter. So you saw how they really were growing up the arrays. So the hexagonal pattern was having more and more layers. And finally, this type of technology culminated with La Boca with close to 300 pixels installed at Apex in 2005. So that was for this type of technology with bolometers. And then for transition edge sensors or M-kits, then all of the detectors, you can see here the Nika 2 on the right that is currently installed at the 30-meter, 3000 pixels. You see that all of the kits can be fabricated on a single wafer. So that really helps for the integration. And at the bottom, you see the cryostat with 3 arrays, then 2 polarizations at 260 and 1 at 150 gigahertz. And at the left is now Scuba 2, also with several wafers for the detectors for the multiplexing. So this is just to give you an idea of what was achieved in this instrumentation in the continuum instrumentation. But unfortunately for heterodyne detectors, it's not the same. So just to show you, the left is for M-kits and the right is for heterodyne. Unfortunately, we see more or less the same size here, 3000 pixels compared to, in this example, is already quite integrated array, 16 pixels at 100 gigahertz. I will explain more what are the limitations, but we are really constrained more by 3D mechanical blocks and components that makes the integration more difficult. So a word on heterodyne spectroscopy. So I will not go too much into detail, otherwise I will spend too much time. Really the main components that we need in a heterodyne receiver, we need a reference signal that we call the local oscillator. So that's something that has to be injected for every pixel. And this reference signal is used with a mixer, usually a superconducting mixer. And then this one mixes the signal you're observing with this local oscillator. And then you have the intermediate frequency at the output at much lower frequencies in the gigahertz range that is then amplified by amplifiers and post-processed afterwards and up to the back end. This very simple scheme with one mixer, one channel. The mixing scheme with when you have only one mixer like this, inherently you are double sideband, meaning that you will have your signal of observation, your band pass, IF bandwidth illustrated here at the bottom. You will have also the image band on the other side of the reference signal or local oscillator. And if you don't do anything, both of them will be superimposed. And at the end in the IF, you will have both sidebands on top of each other. That's the simplest mixer possible. It's a double sideband mixer. So there are many variations of this technology. Then of course, people don't want always to have the two sidebands falling on top of each other. So there have been a lot of progress in millimeter waves, submillimeter waves instrumentation in this field. Double sideband mixer was used at the beginning, but then very quickly single sideband mixers were operational when we rejected one of the sidebands. Then sideband separation mixers were implemented. You can see an illustration at the bottom. Then you need two mixers. You need RF hybrid at the input. You need an IF hybrid at the output with some phase differences. You need to split the LO in two. So you see right away that if you want a better scheme for the receiver, you need to have many more components, and all of them add complication to the receiver. You have a mechanical block for all of those components, and at the end, for one pixel with this sideband separation scheme, you end up with 20 years ago with still a very cumbersome, a lot of space taken by this. But anyway, a lot of progress had been achieved since then, so it was integrated quite well. Before going to that, I will show just a few words on the detectors for millimeter, submillimeter waves. Now the frontier between from few gigahertz to about 100, 115 gigahertz we can have hemmed amplifiers. Hemmed amplifiers at the first active component in the receiver in the cryostat provides the best performance. So the lower frequency receivers, for instance, the question about a 50 gigahertz receiver for NOEMA, that would use amplifiers at the first active component. Then when we get to 100 gigahertz and above, the most sensitive component is a supraconductor mixer, SIS mixer. It needs to be cooled down below 4K, below 5K on average. If you go above 1 terahertz, then HEV mixers are the component of choice. You can also use Schottky diode mixers for any of those frequency ranges, but they're not as sensitive or as performing as other technologies, but they provide a good compromise when you have other constraints like cooling power or satellite missions, then you cannot cool to those low temperatures. But they have become quite competitive anyway, regardless. Then I want to show you a bit how much we have progressed in these past 40 years with the technology. It's a bit hard to show you how this has evolved. So there are many parameters to show. So one is the RF bandwidth for the receivers. The other one is the IF bandwidth, the one I showed you after the mixer. The number of pixels, of course, that's what we're interested today here. And then the sensitivity. So I try to do some 3D plots to show you here in the 80s. So if we take an example, for instance, in many observatories, the blue lines here, the RF frequency range, you would see the bands. So the 3 millimeter, 2 millimeter, 1.3 millimeter, 0.8 millimeter range frequencies here. The IF bandwidth is on that scale there. At that time, we had only 500 megahertz or 1 gigahertz bandwidth. And then the number of pixels is the height. You see it's flat, so it's only 1 pixel. Then there were no arrays back then. Then in 30 years, we progressed quite a lot. So this is actual situation now. You see that the RF bandwidth has increased. So now we can cover everything continuously. So there are also only water lines or atmospheric lines that are not worth covering right now, but we could if we wanted to. And you see that we have started to do small arrays. So for instance, at 100 gigahertz, we have 16 pixels. Many observatories have small arrays already built. At 230 gigahertz, HERA or the 30 meter was also built in the beginning of the 2000s. And at 345 also, there were several projects with 7 to 9 pixels. So that's where we are more or less now. So you see the IF bandwidth also increased to 4 to 12 gigahertz. And then 2030, soon in the close future, that's what we can achieve with high confidence. So the IF bandwidth can increase really to 20 gigahertz. 4 to 20 is the goal. For instance, ALMA development roadmap for 2030 says the goal for that, and many observatories already demonstrated they can have 4 to 20 gigahertz bandwidth, or 0 to 20. We can also start earlier if you want to. The number of pixels also, they will increase. So here I put like 64 pixels at 345, but these numbers that might change here. The sensitivity has also improved a lot. So just to illustrate, for instance, at 100 gigahertz, the noise limit that we can achieve with this technology, it's sideband separation is 1 quantum noise. So you have to see that the intrinsic limit we could ever achieve is 1, and now we're at the limit that we have reached in the 2000s. We're getting close to the 4 times the quantum limit. So this has evolved quite a lot. You can see it a bit also in this scale here. Here I went to a higher frequency to show you better. At 800 gigahertz, we were at 150 noise quanta in 1990, and now we are at 10 times the noise limit at 800 gigahertz and 4 times for the lower frequency bands. This nice plot from the ALMA receivers show this clearly, that between 100 to 900 gigahertz, the lower frequency bands, we are at the 4 times the quantum noise here limit, and the band 10, the 800 gigahertz, we are close to 210 still. So there is room for improvement at the higher frequencies. Okay, so to show you a bit what are the existing arrays so far in different telescopes, I put here this table. You will see that there are many 100 gigahertz arrays, W band, so from 85 to 115 gigahertz, with usually about 16 pixels. So for the large millimeter telescope, green bank, with the one I showed you before, At 230, we have Hera at the 30 meter. 345, there are several arrays also. I think also, yeah, there are at least 3 or 4 telescopes with arrays built. For sub-millimeter waves, also at Apex and Nanten, there are Smart, Cham Plus, and for terahertz range, there on the Sophia there is the upgrade arrays with small arrays there. And the ongoing projects, the people are working on the next generation, more pixels. So, for instance, the Green Bank is working on the going from 16 to 144 pixels at 150 gigahertz. At IRAM, we have the project of building two large multi-beams for the 30 meter at 115 also. So 2 times 25 dual polarization and 2 times 49 at 240 gigahertz. Also, the Sardinia radio telescope has a 16 pixel project ongoing, Nobeyama also. For sub-millimeter, for the CCAT, for the Fred Young's sub-millimeter telescope, there's the Chai instrument planned. And there are also balloon mission Gusto is ongoing, and also Astros, and probably others that I did mention here. So just to show you some of example of the technology, how people are, how various groups are integrating the technology. Most of them chose to produce blocks to put several detectors pixels on them. For instance, this block for the SuperCam, or by 8, so you can put 8 pixels. Then you have 8 times this block to have the 64 pixels. The performance for this one so far was limited IF bandwidth and higher noise temperature than they would expect. So, but they show that it was possible to manufacture many things and integrate quite a lot the components. The other projects, the HARP, JCMT also integrates the horns together here. Here I show you the upgrade arrays. In that case, there is no integration. This is the brute force technique. We put pixels, 7 pixels or 14 pixels, and we don't integrate, but we just, this is really the limit we can do without further integration of the components. To see how this has evolved on Sophia for this upgrade receiver. So more than 10 years ago, for 1 pixel, this is the whole space it was taken, as I was telling you. It really takes a lot of space. And after that, 14 pixels were integrated in more or less the same space, making the first array then in this frequency range. This shows you the Green Bank telescope Argus array at 100 gigahertz. So you see here the 4x4 horns. And this is the Sardinia radio telescope project, also for a 4x4 array in the same range. So another consideration when you want to build large multi-beam systems. So this telescope, the CCAT Prime, I think there will be a talk tomorrow about it, describing it in more details. It was specially designed to the very large field of view, so 8 degrees, with optics cross-dragon off-axis design, so with a very large primary and secondary mirrors. The secondary is almost as big as the primary. And then, of course, you can place a lot of detectors. And in that one, so the Heterodyne Instruments built by Cologne, or the Chai instruments at 480 and 810 gigahertz with 64 pixels each. And you see they also will integrate by blocks of 4. So try to have 4 various layers of 4 pixels. I put here some references that a lot of these presentations I show you are available in the front-end development workshop that was held a few weeks ago. So you can find it online, and there was a nice review on all of the work I'm showing here from various groups. So the integration of components. So at IRAM at NOEMA and the 30 meter. So we came from 20 years ago. The components, for instance, this was a mixer at 325 gigahertz, where you see the sideband separation. The various blocks are here, the mixer blocks there, coaxial lines, the hybrid line here. And then it was all integrated in one block. That really 10 years ago, or 5 years, yeah, about 10 years ago. Then this allows now to really consider stacking them together, and the plans for the IRAM multi-beams are then with this form factor for the mixer blocks, integrating most of the components. It's now possible really to integrate the rest all together with the amplifiers, the mixers, and the 100 gigahertz. We have automate transducer for the polarization splitting, and the 1.3 millimeter arrays will have a wire grid to separate the two polarizations. So there will be two of those in a cryostat. So this is the next generation arrays for the 30 meter. We started also doing in the framework with the RadioNet project called ITRA in the past 3 years, demonstrators for those arrays. So we built in collaboration with Fraunhofer Institute, Max Planck in Bonn, and INAF, a demonstrator array that can be populated with up to 3 by 3 pixels at 100 gigahertz with HEMT amplifiers. And then more interesting for us was to do this one line of the full multi-beam, so the 7 pixels at 230 gigahertz, or integrated in a closed cycle cooler, and is being integrated and tested as we speak. Other groups have thought about integration in different ways. So I mentioned this one from Chris Groppe group, the kilopixel Pathfinder at 60 gigahertz with 16 pixels. So it's a kilopixel Pathfinder, meaning that the aim of the project is to build a 1,000 pixel array. And their concept is to do it as simple as possible with unit cells. And then it's double sideband mixers, so no complications. So just take one mixer, one amplifier, integrate things as much as possible in this unit cell. And that was the concept they showed. Other concepts are here using platelets fabrication for the components. So still, the main problem with all these millimeter waves signal transport is that we often use waveguide transport. So we need metal structures. And these people here with the platelets, so you can, instead of building the blocks in a milling machine, then you have several layers, 5 or 7 layers of metal, where you then put all your structures, like the automat transducer, the mixer blocks, or even the horn can be built with these techniques. So this Canadian group here is working on this concept of doing arrays with platelets, to ease fabrication especially. Another idea, very promising also, is the planarization of the front end. So the left shows you what I'm talking about, 3D mechanical blocks that it takes a lot of space. So here you see the automat transducer on the left, then the 2 sideband separation mixers here. These can all be put in a 2D planar circuit. So the automat transducers and the mixers and the rest and the hybrids can be fabricated there. So this group in Japan, so Wenlei Shan, they demonstrated a 4-pixel array using this technique. So this here they show how it works for 4-pixel modules. So you stack the things like this, so the electronic circuits, these planar circuits, and then you can potentially then build 100-pixel arrays quite easily, or smaller arrays for interferometers. So that's an interesting concept. Another thing I like to show you is people also working to split frequencies, so to observe various frequencies at the same time. So we talked about dual band observations. So that's already done in various places where we observe 2 separate bands with a dichroic or some kind of separation. And this group here, for instance, in Japan, again, they build a receiver for the Osaka 1.85 meter telescope, where they split the input signal to observe 4 bands at the same time. So to observe various transition of isotopologues of CO with very wideband IF signals also. So this is already demonstrated. And also interesting is they are building a prototype of a 7-beam 2 polarization to cover 70 to 116 gigahertz, but splitting also so to observe the 3 bands at the same time. So in that range, so they will have the areas marked in yellow, green, and blue here. So this is a bit of a pragmatic approach because they do it like this, so they're not limited by the backend bandwidth, so they can observe almost the whole band or the band of interest instantaneously. Because with the HEM technology, you can have all of the band at once, but you still need to have the backend power to process all of the band at once. So instead of waiting for that technology to be ready, they decided to let's do it like this now, so we can already observe all of the band at once or close to it. So another thing just to show you, there are also thoughts about building multi-beams for interferometers. But before that, for space, of course, there are Martina Wiener will probably talk about that on Thursday, about multi-beams or for space missions like the Origin Space Telescopes. But for interferometers, they also started to think about it and even have feasibility studies. And last, I think the large single-dish telescopes, for instance, Atlas, I think the goal will be to have thousands of pixels. I think Claudia will probably talk about it tomorrow. For the interferometers, just to show you that the SMA, the wideband millimeter array, the VSMA as it's called now, they are planning to build 7-pixel 329, 356 GHz instruments for their interferometer. Also, ALMA has some feasibility studies to do 3x3 pixels for the band 9 cartridge. So they started to do the studies to show that it's all possible and doable. And for NOEMA, it hasn't started yet, but I think people are starting to think about it. It's in the mind of people. And just to conclude on this, what would be the ultimate instrument? Of course, in the further future, we would like to cover all of the band at once. If we talk about millimeter to millimeter waves, with the widest IF possible, high pixel count. So just to show you, this is just a picture showing where we are now and where we want to go. And of course, that's what you all want here. So the conclusions. I think there's nothing really fundamental now that prevents building large arrays, moderately or large arrays. So I think the detectors are mature enough. They're very sensitive. We have enough local oscillator power. The crusted cooling power is not really a problem. It can be, we can put several cooling machines to cope for that. We need still to go for more integration if you want to go for even larger arrays for like thousands. The limits are, and I mean, there is nothing fundamental. Now it's mostly engineering challenge. So putting all together, there's nothing really blocking it. But I put it here with the dots, the funding. This is, of course, if there was enough funding in many institutes, that would help. Just to show you here in Europe, we are probably a dozen groups working in instrumentation for radio astronomy, operating about 10 telescopes worldwide. So it's not a lot. And just as a comparison for the industry, now they are getting also to the millimeter to millimeter waves with the 5G, 6G, the car radars, terror security, many more. And they have about 100 to 1,000 times more power in budget power and people and resources, and they're already getting very fast. For example, Nokia is building a 384 pixel a V-band at 100 gigahertz phased array, and they are starting to have very good results for that. So the conclusions here, as I said, so I think we can really make moderately large arrays, 100 pixels. So there is really no fundamental limit. We need a bit more funding, more groups working for that. I think after ALMA and Hi-Fi developments, there was a bit of a dip in far infrared projects, and we lost momentum in the technology area in various groups. Some other groups stopped doing things. The industry, with all this, their funding, and I think we also should take advantage of what they are achieving. So in the sense of miniaturization and integration, I think that's it.
Thank you very much, Christophe. So we have some questions from Jérôme.
Yes, so in your 3D comparisons, the current one, you have much less pixels at 3 millimeters. Now, the intermediate one, exactly. You have much less pixel in this one. You have much less pixel at 3 millimeters than at why is it?
Oh, yeah. This is just for the wavelengths because of the component, the horn size, the corrugated horn for a given cryostat size. That was the main limit in that plot, was that it was because then it takes more space in a cryostat for the horn itself.
Yeah, but do you mean that it's not possible to be big cryostat bigger?
If it's possible, if also the optics of the telescope is done for that, so it has to go together.
Okay, so we have questions from Quentin.
Yes, I have two questions. One is kind of practical and the other one is fundamental. The first one is, what is the time scale to get multi-pixels at ERAM?
So I would say it's really hard to put a number because we're working with many projects and we have to complete NOEMA, and I think 4 to 5 years to have really the first tests and validation, probably not of the full arrays, but the first polarization or part of it. So I would say 4 to 5 years.
Okay. And the second one is about one of your last slides. When you mentioned that now there are interferometers that start to think about multi-pixels receivers. But in that case, how do you correlate the signal? Do you have to do it pixel by pixel? So if you have 9 pixels, you have to do it 9 times, or?
Yes, I think maybe Jerome is better for that, but I would say probably yes. You have to do it pixel by pixel.
Yes, I think you'd have to do it pixel by pixel. The difficulty, so there are challenges that are technical, but there are also challenges in the calibration.
Okay.
And not just in the calibration algorithms, but in the techniques to calibrate. So how to calibrate phase and amplitude in a multi-beam.
Okay. Okay, thanks.
Thank you. So we have 2 more questions, one from Nicolas Giver.
Yes, well, my question was a bit following what was just said. I mean, behind this, you will have billions of channels. I guess you expect to keep the higher spectral resolution. So how do you think we can anticipate the issues of calibrating billions of channels, and we have the capacity for correlators on FTS and so on?
So there are 2 different questions. The first question is backends, and for this, I'm not sure. I think we should discuss with on that. But for calibration, I don't think this is an issue. It's a question of parallelising the calibration, and today we have computers that are parallel by nature. So
in real time, it will be okay. To do it in real time, it will be okay
so for we've been ready for 5 years since the last 5 years for the 25 pixel multi-beam.
So longer time.
Okay, so there is a last question by
it's
Claudia,
not completely true.
by Claudia Ciccone.
So I have the first question is, what do you think it would be the cost of a 1,000 pixel heterodyne focal plane array in, say, 5 years?
The cost, if we had money to build it, so how much would we need it?
Yeah.
Well, I think $100 million.
100 million.
Yes.
Okay.
Because
yeah. And so this is in 5 years, and in 10 years?
Yeah, then
same. Okay.
No, probably less.
Less.
Sure. I mean, if you have more time, but just to put to show the instrument that they are building for Sophia, for instance, there are $20-30 million for these large arrays. For Continuum, Hermes, for instance, went to 30 or 40 million and was cancelled somehow. So.
And the second question is, do you think these kind of instruments could have a plan for an internal wobbler in those cases where you can't wobble the secondary mirror?
Yes, I don't see why not, but not in the cryostat, but in the receiver cabin or somewhere like this, yes.
So I heard there was ideas to, so, you know, in the optics, in the relay of the instrument itself, where you form an image of the pupil. If you place a wobbler there, effectively, it's like if you're moving the entire telescope. So it would be interesting for a telescope like Atlas, where we would have a 12-meter secondary mirror that we can't wobble. So
I think it's maybe possible. Yes.
Okay, thank you. So a last question by Philippe.
So I wanted to ask you, you said that I mean, one of the gain is the integration, I mean, the reduction of the size of the different component. And from the question we had, it's a very naive question. Is the size of the feed is a limitation that will prevent us from having, I mean, does it give a limit in the size of the camera that we can have?
Yes, depending on the optics, how you choose to do it, the corrugated, the horn itself, yeah, you cannot go closer to it sets a limit on the space in between the pixels.
So this gives you a size limit that you will never be able to.
Well, if you use horns, but then you can use other type of. You can have quasi-optical designs. You can, like continuum cameras, you can also couple differently. The problem is that we usually use corrugated or smooth wall spline horns that are have a very good coupling, close to 99% cauticity. So we really don't lose almost anything, don't couple anything from the site. Whereas the other alternatives are not as perfect. So you increase the noise performance, you degrade the receiver performance. So it's a trade-off. So if you want to go for many more pixels without horns, you could do it, but paying a price in the efficiencies. But if you have more pixels, then maybe you gain.
Yeah, and just maybe another question about the flexibility on the frequency range that you can observe. I mean, you showed in your last slide that you could observe some plan to have a very wide band where you would put like windows. I was more thinking that this would be done in the back end. So it's also possible to do that in the front end. And then you could have, because I mean, apart from the field, which are very blended in lines, for example, in the extragalactic, it would be very interesting to have windows that you could put like with a backend on some specific lines, because otherwise it's just noise. In fact, I'm not interested to map that.
Yeah, no, that's right. There are several possibilities. So that's you can have a front end that is very wideband, and then as you said, the backend could select where to go. Or the ones I showed, some of the front ends, they decided to put put the limits in the front end side. So you can choose where you want to do it. But I agree that that's one possibility. If we are limited in backend, we can do that.
I would like to stress something about interferences. I have written a little note on that. I mean, not long ago, we had a message from ESA, which was telling us, cheer, folks. The very first satellite with a transmitter on board in the W band, right, has been launched and will start to operate. So I think this time it's not just interferences on the ground, that it's interference which come from the sky. And I don't know exactly how far this will go and how many satellites will come. But since we are thinking about the year 2030 and beyond, this is something we have to worry about. And just to say it, I would like to say that with a single dish telescope, it may be more difficult to counter that, especially if there are many transmitters or widebands. But maybe with interferometers, that means multi-beam receivers or interferometers, that will make the things much easier to solve.
Yeah, I agree. That's completely true. That it's really worrisome to have all these new technologies, communication coming to the millimeter wave. So as I showed, this Nokia development at W band phased array. So they're already starting to come to 100 gigahertz. And yeah.
Okay, thank you very much to everybody for this discussion.